Bismillahirrahmanirrahim. I am Dr. Abdullah. Today we will explain the fourth unit entitled Belt Drive. This lecture is among the lectures that are taught within the Design of Machine Elements course. Today we will talk about the following outline. The first section of our discussion will cover an introduction on belt drive. In the next section, we will examine the belt drive's operational setting. Thirdly, we will talk about belt drive's abilities to transmit power. Fourthly, we will go through how to design a system of belt drive. Finally, we will talk about installing and maintaining belt drive. Typically, power and motion are transferred from one rotating element to another via a mechanical drive, sometimes referred to as a power transmission. Mechanical drives include worm gear drives, belt drives, chain drives, and more. They can be generally divided into flexible, rigid, or non-flexible power transmission drive. A flexible intermediate element such as a belt or a chain sits between the driving and the driven shaft in a flexible drive. The translational motion of the belt or chain is first changed from the rotating motion of the driving shaft to the rotating motion of the driven shaft, and then the reverse is done. The rotary motion of the driving shaft is directly translated into the rotating motion of the driven shaft in a rigid drive, such as a gear drive, via the direct contact of pinion and gear. The Fisher's analysis and design of belt drives will be all covered in detail in the chapter. Our talk will begin with a brief introduction to belt drive. One of the most common forms of flexible drive is a belt drive. They are frequently employed in automotive or industrial drives to transfer a greater rotating speed of a single component across a long distance to a lower value. An electric motor supplies the driving machine with the necessary power. A power transmission system is used since an electric motor's typical operation involves high speeds and low torque, which are inappropriate for the machine being driven. Belt drives are often employed at the first stage from the power source in a power transmission system. To meet the driven machine's speed requirements, gear reducers and other drives with suitably specified speed ratios are employed between the belt drive and the driven machine. Compared to gear drives, the tolerance on the center distance is less important for belt drives since they are used to transfer motion over relatively large distance, and the configuration of the driving and the driven shaft is much more flexible. Although a belt may slide when it becomes overloaded, it offers some protection for the driver and the machinery it drives. Belt drives also provide the benefits of easy operation, straightforward design, and shock absorption. Their application frequently streamlines machine design and significantly lowers manufacturing and maintenance costs. The inherent elastic creep between the belt and the pulleys, except for timing belts, causes the speed ratio of a belt drive to be inaccurate. Belt life may also be shortened by belt slippage. In addition, the coefficient of friction and interfacial pressure between the belt and the pulleys limits the transmission of power and torque. A belt must be installed on pulleys with the correct initial tension in order to assure effective operation, and belt tensioning mechanisms are necessary to keep the initial tension in belt drive. A driving pulley 1, a continuous belt 2, and a driven pulley 3 make up a standard belt drive. A flexible band that wraps around two wheels and transfers power and motion from one to the other is called a belt. Pulleys are wheels with a flat profile, whereas sheaves are wheels with grooves. The small driving pulley is put on the high-speed shaft when a belt drive is used to reduce speed, which is typical in industry. The large driven pulley is attached to the driven machine shaft. The torque will rise according to the speed drop. Machines must have features that allow for belt replacement and adjustments since belts are in finite loop. This slide displays two common belt drive configurations: a cross belt drive on the right and an open belt drive on the left. When the driven pulley must rotate in the same direction as the driving pulley, an open belt drive is employed. When the driven pulley must rotate in the opposite direction as the driving pulley, a cross-belt drive is used. Because of cost and efficiency, several types and sizes of belts are available for different load levels. There are primarily 4 types of belt configurations, that is, flat belt, V-belt, round belt, and timing or synchronous belts, each with its individual characteristics. The simplest and most affordable belts have a thin rectangular cross-section and are called flat belts. They are made to function using cylinder-shaped pulleys. The working surface is the area that makes contact between the belt and pulley. Frictional force on the working surface limits the driving force. At high speed and relatively low power, flat belts work well. Flat belts expand excessively when high power are to be conveyed, making them uncompetitive with V-belts. V-belts often have unending cross-sections with trapezoidal lengths. V-belts need sheaves or grooved pulleys. The V-belt wedges firmly into the V-shaped groove due to the geometry of the cross-section, and the two contact sides are working surfaces. As seen in the lower left illustration, a ribbed belt combines the features of a flat belt with a V-belt. While the V-belt segment secures the sheave, the flat belt section carries weight. Belts with rib increase their ability to bear a load and reduce excessive bending strain. Round belts, which have a circular cross-section and are only suitable for light operations, are mostly utilized in household appliances and machines for textile industry. They may be bought in a variety of lengths or can be customized for your needs. They can be attached with a staple, a metallic connection, glue, or welding. Timing or synchronous belts, which are endless flat belts with a series of uniformly spaced tooths on the inner side of the circle and are intended to mesh with complementary toothed wheels or sprocket to reduce slippage, are available in a variety of materials. They are utilized for synchronized power transmission to guarantee that the driven sheave constantly rotates at a consistent speed ratio to the driving sheave. A timing belt's ability to transmit power is constrained by its tensile strength and the cogs shear strength. Timing belts have the high speed properties of flat belts and a power capacity that is comparable to chain. The range of industrial uses for V-belts may be the greatest of the belt kinds listed above. The reliability and life of various V-belt designs have been extensively tested and standardized. The belt industry uses the datum weights system for both standard and narrow V-belt arrangement. The beach line indicated in the diagram as NN serves as the belt section's neutral axis. As the belt curves around sheaves, the beach width BP, also known as the beach line width, remains constant. At the locations where the neutral axis of the belt contacts the groove, the datum width of the V-belt groove BD is measured. As a result, BD equals to BP, or the datum groove width BD is the same as the beach width BP. As a result, the beach diameter DP and beach width BP and the datum diameter DD and groove width BD are the same size. Since the neutral axis of the belt contacts the sheave groove at the sheave diameter D, also known as the beach diameter DD, equals DP equals D capital. The belt and the sheave move at the same linear speed at beach diameter. The belt length is known as the datum length LD when the sheave diameter is defined as the datum diameter DD. Both the datum diameter and the center distance affect belt datum length. The nominal value of the equivalent groove angle phi1 between the two sides of the V groove on a sheave range from 32 to 38, whereas the wedge angle phi of a V-belt is 40. Due to its design, the V-belt wedges tightly onto the groove when in use, increasing friction and enabling the transmission of a large torque before sliding. In terms of cross-sectional size, length, power rating, and sheave diameters, V-belts have undergone substantial standardization. A standard or conventional V-belt and narrow V-belt are two main categories. At the same beach width BB, a narrow V-belt has a higher height F than a conventional V-belt, in contrast to narrow V-belt, which have a smaller cross-section and are labeled SBZ, SBA, SBP, SBC, C depending on their cross-sectional size. Standard V-belts are identified by an alphabetic letter for kinds Y, Z, A, B, C, D, and E. Each size is appropriate for a specific power range. Standard V-belts may be made into many configurations. Belt must be robust in tension, flexible for bending, light in weight, and offer enough friction against sheaves since they are susceptible to tension, bending, and centrifugal forces. V-belts, which are frequently made of leather, fabric, rubber, and synthetic materials, offer a quiet, compact, and robust method of power transmission. This slide demonstrates how a standard V-belt is built. A belt's high durability is provided by the outside fabric cover. In order to boost the tensile strength of belts, high-strength cords typically constructed from natural fibers, synthetic strands, or steel are positioned near the beach line of the belt cross-section. The strong rubber compounds that these cords are embedded in provide the belt the flexibility it needs to pass around the sheath. A belt is built to satisfy certain design needs by combining several parts.